Good morning, students. Today I will start a new chapter of your syllabus, that is electromagnetic induction. Okay, so before we start the electromagnetic induction, we need to understand what do you mean by the term induction. What is induction? Induction is basically an influence of a magnetic field or electric field to a non-electric or non-magnetic substance in the presence of a magnetic or electric substance, right? So this is the in general concept of the induction. Let us understand this concept using a diagram. So if I consider a magnet here, it is a magnet, bar magnet, right? And now if another suppose this is an iron rod. So due to the presence of this magnet, this iron rod will becomes magnet for some time. As much time this magnet is present in front of this iron rod will act as the magnet. Okay, so basically this is the induction. Due to the presence of this magnet, this iron rod acts as magnet. So this process is called the induction. Okay, so same thing is happening for the electromagnetic induction. So electromagnetic induction means their electric and magnetic two fields are consecutively present there. That's why it is called the electromagnetic induction. Okay, hopefully it is clear to all. Next, from this chapter, first concept is that magnetic flux. So what is this magnetic flux? Magnetic flux is that if we consider, suppose we are considering a plane and this plane is perpendicular to some uniform magnetic field. Okay, so here are some uniform magnetic field and this is basically magnetic field is defined by B. Okay, so as the plane is there and this plane is perpendicular to this uniform magnetic field and the area of the plane, then this area of the plane is called the magnetic flux linked with that plane. Okay, so this magnetic flux is defined by this sign, that is the phi. By using this phi sign, we can implement or we can represent this magnetic flux. Okay, now suppose, so if the area is A, so phi will be basically B into A. Clear? Now here I have drawn this magnetic field straightway perpendicular. Now if I consider or if I draw this magnetic field like this, suppose this is a plane is there, a plane is here, okay, and now the magnetic field is like this. Like this. So this is the plane and magnetic field is acting like this. So then what will be the magnetic flux of this plane? We will draw a perpendicular from here. Let us consider that is theta. So therefore the phi will be basically BA cos theta. Okay, so this will be BA cos theta. So for this condition, what we can say? We can say that if the magnetic field B, instead of being perpendicular to the plane, make an angle theta with the perpendicular to the plane, then the magnetic flux linked with the plane will be equal to the product of the component of the magnetic field perpendicular to the plane and the area of the plane. So therefore BA cos theta. Okay. Now if phi is positive, then or when we can say that this phi will be positive, basically when the if the outward normal of the plane is the same direction as the magnetic field. So the normal, if the normal of this plane is at the same direction to this magnetic field, then it will, phi will be positive, and if the normal is opposite in direction, then this phi will be negative. Hopefully it is clear to all. Now the next is that if a coil of area having A and having a coil having area A and number of turns be N, then we can say that the magnetic flux density, and if the magnetic flux density B is there, then we can say that phi equals to NBA. Okay. So now what will be the SI unit of this magnetic flux? The SI unit of magnetic flux phi is basically defined as Weber. The short form will be WB, as B equals to phi by A. From the equation phi equals to BA, we can write this. Therefore sometimes this B or magnetic field is denoted as magnetic flux density. Okay. So then the unit will be Weber per meter square. Hopefully it is clear to all. Next, what will be the dimension of this phi? Let us consider. So phi equals to basically BA. Okay. Now from the formula, force on a current carrying conductor in a magnetic field, what we can write? We can write BIL. Now from there B equal to F by IL. Okay. So phi equal to, we can write FA by IL. Okay. Now what will be the dimension? So dimension phi will be basically, so force is there, F is there, so dimension of force ML T to the power minus 2. Area is there, that is nothing but L square, and in the denominator I is there, I is defined as A, and length is L there. So if we cancel out this L cube, it becomes L square. So the dimension will be M L square T to the power minus 2 A to the power minus 1. So this will be the dimension of phi. Hopefully it is clear to all. Now the next topic is induced EMF. First, scientist Faraday has discovered or proposed this concept of induced EMF. So what is it? Basically Faraday discovered that whenever the number of magnetic lines of force or magnetic flux passing through a circuit changes, an EMF is produced in the circuit. Okay. So what I am saying, that suppose a place is there, through this the magnetic lines of force or the magnetic flux is passing by. Okay. So what we can say, if this magnetic field changes, if it is a circuit, and if the magnetic flux changes, then in that circuit an EMF or electromotive force will produced. If this circuit is closed, a current will start to flow through it. So what I have said, if it is a circuit and through this circuit if the magnetic lines of force is moving on. Now if this magnetic lines of force or magnetic flux changes, then an EMF will introduced or induced through this circuit. If it is open, then it will remain as EMF or it will remain as voltage, and if it is closed, that voltage converts into the current. Okay, so this EMF is called the induced EMF. And the current which will produce in this coil is, or in this circuit, is called the induced current. Okay, so this happens when the magnetic flux phi changes, right? So this phenomena is called the electromagnetic induction. Okay, hopefully it is clear to everyone. Now, how this phi, I have said for the electromagnetic induction, phi should be changed. Phi there, that is electromagnetic flux should be changed, right? Then what is the parameters, or how we can change this flux? First thing is that we can change the flux by moving the circuit. If we move the circuit, suppose the magnetic field is there, but if we move the circuit, then the flux will change, right? Second is that suppose if a coil is there, another coil is there, and through that coil or another magnet is there, and a coil and a magnet is there, and now if we move this magnet, then the magnetic flux will change inside that coil. Okay, and another thing is that, if we change the current flowing through that coil, then also the magnetic flux can be changed, and if we move the coil, then also the magnetic flux can be changed. So by these four processes, first of all, that the moving the magnet relative to the circuit or relative to the coil. Second is that by changing the current in the neighboring circuit. Third is that by changing the current in the same circuit, and fourth is that by rotating the coil of the magnetic field. So in this way we can change the magnetic flux. Okay, so today I am ending this. In the next class I will continue with the Faraday's law of electromagnetic induction. Okay, thank you.